So we have to consider particles, a system of particles. These are n particles and they are arranged in m boxes. I will just draw a box here. This is box number 1 and this box represents the energy level of the particles that are contained in this box. The first box that can contain any kind of particles among these n particles, they can be inside here, and if they are here they have some particular energy level. We have another box and all the way up to, let's say, m boxes. In this video I will revise the concept of binomial coefficient. Let's say that we put n1 particles inside this box and we choose them at random, and then n2 inside this one and m inside this one. How many choices do we have for the first box? Well, we have at first n particles, right? So we have n possible choices for the first particle to put inside here. Then we have n minus 1, then we have n minus 2, and we have to multiply these terms. Why? Because we have all possible configurations, and these configurations just multiply each other if you just count them. All the way up to n minus n1 minus 1. Why? Because we start here at n minus 0 if you want. 0, 1, 2, 3 until n1 minus 1, it's n1 choices because I have to put n1 particles. And these are the choices, but also consider the fact that we must divide this number by another number because we are counting too many times. Why? Because, for instance, let's do this very short example. If we have two equal dots, let's say that they are exactly the same. If I label them just for sake of simplicity 1 and 2, I can put the second before the first and I have, for instance, this arrangement 2 and 1. But when I look at the dots, I see no difference from the first one to the second one. So these two are the same and we must count them only one time, right? In general, if I have n dots and they are the same dots, I cannot tell the difference from them. And how many arrangements can I make? Well, I just have to count. For the first particle I can choose between 6 of these because they are 6, just in this case. For the next one, of course, I have 5, then I have 4, then I have 3, then I have 2, then I have 1, right? So this number is also called factorial, so I can simply write this like this, 6 factorial. In this case here, because the particles are considered to be equal, I mean, if I look at this one and this one, they are not different. So I have n1, so I have to divide by n1 factorial. I will rewrite this in a more suitable form. If I take the numerator, I can rewrite it like this, so equal to, I can rewrite it as n times n minus 1, dot 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 all the way down to 1, and of course I have to divide by n minus n1 times n minus n1 minus 1 because I have to get rid of the terms that I have added here, and then I have n minus n1 minus 2, you get the idea, all the way down to 1, and then also I have n1 factorial. These guys here can be rewritten as the numerator is n factorial and then I divide by n minus n1 factorial and 1 factorial. This is defined as the binomial coefficient like this. We put an n here and then I have an n1 here. So this is read as n choose n1.